This video describes a new procedure in Statgraphics Centurion version 17 for analyzing one-way repeated measures designs. Repeated measures experiments are experiments in which more than one measurement is made on the same experimental subject. There are usually two types of factors: within subject factors, which have multiple levels for each of the experimental subjects, and between subject factors, which are factors that have only a single level for a particular subject. This slide shows a typical one-way repeated measures design. It's from the excellent book called Analysis of Messy Data by Millikan and Johnson. In this experiment, 8 patients were given the same drug. It was a drug designed to affect their heart rate. The patient's rate was measured right before the drug was given, that's time t1, and at 3 5-minute increments thereafter. What we're hoping to learn from this experiment is, first, does the drug significantly affect heart rate? Secondly, if it does, how does the effect of the drug change over time? I've loaded the data into the Statgraphics datasheet. The heart rate measurements for each patient are in a separate row. There are 4 columns corresponding to the 4 times at which the rates were measured. To analyze the data, I'll select Compare from the main menu. I'll then choose Analysis of Variance, Repeated Measures Designs, One-Way Repeated Measures ANOVA. There are 2 ways the data could have been structured. In this case, I've put each of the time periods in a separate column. There's also a data and code column structure in which all of the measurements would be placed in a single column. But for this example, it's easier to use multiple data columns. To run the procedure, I'll place in the response field the column names T1 through T4. In the subject field, I'll put the column name patient and then press OK. There's nothing to change on the Analysis Options dialog box, and on the Tables and Graphs box, the defaults will be fine. This will open up a new analysis window with 2 tables and 2 graphs. The first pane I'd like to look at is the profile plot in the upper right. This shows the heart rates at the 4 time periods for each of the 8 patients. You can see that in general, the heart rate followed the same basic pattern for each patient. The second thing to look at is in the upper left corner, where there is an Analysis of Variance table. The most important line is the line for condition in the factor sums of squares table. Since the p-value here is very small, it indicates that there are significant differences between the means at the 4 time periods. A significant complication arises when you're analyzing repeated measurements. That is, the random errors from one time period to another for measurements made on the same experimental subject may not, and usually are not, independent. This could invalidate the standard F-tests in that ANOVA table unless the data exhibit a property known as sphericity. A sufficient condition for sphericity to be present is compound symmetry. Compound symmetry implies that the variances and covariances of the repeated measures are equal to one another. A common solution to this problem, which we'll apply, is first to use Mauchly's sphericity test to determine whether or not it's reasonable to assume that sphericity is present. If it's not, then we can do one of two things. We could apply an epsilon sphericity correction to the degrees of freedom in the f-test, or we could perform a multivariate significance test. Let's return to Statgraphics and put away the standard ANOVA table. The second text pane I asked for gives various sphericity tests and adjustments. You'll see at the top Mauchly's test. If the p-value of Mauchly's test was below 0.05, it would indicate a lack of sphericity at the 5% significance level. In this case, the p-value is quite large, so it would be reasonable, in fact, to assume that sphericity existed. If Mauchly's test gave a significant result, then we could correct the f-tests that we performed in the standard ANOVA table by estimating an epsilon correction. Now there are three different epsilon corrections: a Huynh-Feldt correction, a Greenhouse-Geisser correction, and a lower bound. There are various theories about when and which of these corrections to use. Probably the Greenhouse-Geisser is the most commonly used correction. So if we got a significant result in Mauchly's test, we'd go to the tests of within-patient effects. You will see a line for Greenhouse-Geisser. The degrees of freedom column shows the epsilon correction made to the standard f-test. A particular significance is the p-value. It's interpreted the same way as it would have been in the standard ANOVA table. P-values less than 0.05 indicate significant differences between the means at the different time periods. For smaller data sets, the Greenhouse-Geisser type tests are usually the most powerful. If we had a lot of data, we might prefer to do a multivariate test. These are the same tests that would be done if you were doing a ANOVA. You see 4 different tests, which for this particular sample turn out to be the same. They could, however, be different. Each results in a p-value, interpreted again the same way as all the p-values we've been looking at. Below 0.05 indicates significant differences between the means of the 4 time periods at the 5% significance level. Since all of the tests indicated that there are significant differences between the means at the 4 time periods, we should now go on and examine the pattern of those means. There are a number of ways we could proceed. First off, we could use a multiple range test, such as Tukey's HSD test, to determine which means are significantly different from which others. We could instead use a mean rank plot with Bonferroni intervals, which would not assume that the error terms follow the normal distribution. A third approach would be to assume a smooth trend over time and estimate its form. Let's return to Statgraphics again, and this time double-click on the bottom right corner. Here you see by default a plot of means with 95% LSD intervals. I'm going to press the right mouse button, go to Pane Options, and ask for Tukey HSD intervals instead. Tukey intervals let me do pairwise comparisons between all pairs of means at the 95% level. Any intervals that overlap indicate that the means at those two time periods were not significantly different. Any intervals that do not overlap indicate a significant difference between those two means. In this case, you can see that the mean of time period 1 does not overlap time period 2 or time period 3. That interval, however, overlaps time period 4. Consequently, time t1 is significantly different than time t2 and t3, but not significantly different than t4. Likewise, the mean's heart rate at times t2 and t3 are also not significantly different at the 5% significance level. If I was worried that there might be outliers present in the data, or that the errors followed some other pattern than a normal distribution, I might prefer to take a non-parametric approach. If I go to the button that lists the available tables and graphs, I could ask for a Friedman test and a mean rank plot. This table and graph go hand in hand. If you take a look at the Friedman test, what's being done here is that the data for each patient are being ranked. Each time period for each patient gets a rank of either 1, 2, 3, or 4. We then compute the average ranks at each of the time periods and perform a statistical test to see if the mean ranks are significantly different. In this case, the p-value is well below 0.05, indicating a significant difference between the mean ranks at the 4 time periods. We can plot these mean ranks with 95% Bonferroni intervals. This lets us do an experiment-wide comparison of all pairs of mean ranks. It works the same way as the Tukey HSD intervals. Intervals that overlap, such as T1 and T4, indicate no significant difference between the mean ranks at those time periods. Intervals that do not overlap, such as time T1 and T2, indicate a significant difference between the mean ranks. The intervals here are a little wider than Tukey's intervals, and you do see that the interval for T2 and T4 overlap, although just slightly. Technically, the mean ranks at times T2 and T4 are not significantly different from one another. However, the general conclusion here is very similar to what it was using Tukey's HSD intervals. The third approach to modeling the effect of the drug over time is useful if the different conditions are equally spaced. In that case, I might consider fitting a smooth function showing the effect of the drug over time, a continuous function. To do that, I can go to the list of tables and graphs and ask for a trend analysis and a trend plot. The trend analysis will fit different order polynomials. In this case, since there are 4 different time periods, it fit a linear trend, a quadratic trend, and a cubic trend. The p-values in the rightmost column indicate whether the highest order term in a particular polynomial is statistically significant. In this case, the linear term is significant, the quadratic term is significant, but the cubic term is not. This suggests that a good model for the change in the means over time would be a quadratic model. I'll double-click on the trend analysis table to put it away, and double-click at the bottom right to display the trend plot. Initially, it's fit a linear model. I'll push the right mouse button, go to Pane Options, and enter 2, so it displays a quadratic. This model fits the data quite well. It implies that the heart rate will go up until sometime between T2 and T3, after which it will go back down again. As you can see, there's much to be learned by analyzing a repeated measures experiment.